I haven't really detailedly introduced the approximation. Maybe some of you already know, if you're just using traditional pin physics from neural network, basically just using a neural network to approximate the solution with the input, the spatial coordinate, and you have a neural network, you just approximate that, and finally the neural network is parameterized by a set of trainable weight function. In our framework, we propose a so-called neural partition of unity. The idea is that we want to combine the predefined function or its trainable function. But the idea is that given a lot of mechanics problem, we already know the feature. So why don't we just encode this feature in the neural network model such that it can allow more efficient training, more accurate representation? And I will show you some example. For example, for this large deflection of cantilever beam. Usually this is a very challenging, of course, it's not a challenging problem for finite element, but still it takes some time for graduate students to learn the nonlinear finite element, right? And for pin, usually it doesn't get a very good result given the training issue, the effective training issue. But our model, you can refer to our paper here. Our model actually is able to obtain quite a desirable result compared to the finite element solution, as you can see here. We also take the one snapshot at the center to compare the result between finite element and our model. You can see all this, even the stress solution we match quite well. And as I mentioned, the framework can be really readily extendable. We even can, change the constant model to the elastoplasticity model. So here we're using the J2 plasticity model with associated flow rule here. Then we our NIM model is a so-called neural integrate mesh-free model. It's we developed 2 years ago, and as you can see, we compare to finite element, we can get quite satisfactory result, and at this level of accuracy. Okay, but I want to emphasize that here we are not trying to say we try to using this neural network based model to replace the traditional simulation method, because it's not promising to do that in terms of the computation time, because right now the high performance architecture is really built for the conventional solver. But later I will show you some like a very exciting update by using GPU. But here we are not trying to do that. The real selling point here is that we want to do the inverse modeling problem such that we can characterize some hidden parameter that traditional method cannot obtain. And on the same time, our model have very nice forward simulation efficiency and accuracy. So let me just give you a problem, give you a setup of problem for this inverse modeling here. So let's look at this. This is a hyperelasticity material. Let's focus on, so you can make synthetic material parameter distribution. So this is Young's modulus, is heterogeneous, and this is highly random, right? This is a relatively simpler. This is Gaussian distribution, and I just want to say, in this setup, we only collect some strain measurement, and we have no knowledge about the Young's modulus distribution. And by our framework, this is for the Gaussian is easier. Then you can see by our framework we can identify the unknown distribution of Young's modulus in a very high level accuracy. And even for this case, for this really random scenario, we are also provide. This is very excited by upon the publication. This is state-of-art inverse modeling result. Is like the relative error is less than 8%. So we only only using the strand data, and we don't have any direct measurement for the Young's modulus. Okay, so given the time limits, I will just give very high level idea. I prepare actually quite a lot of slide, but I just later realized it only 30-minute talk. And if you still remember, the motivation for us is want to promote our computation framework to the challenging geohazard geophysics problem. So we take a step further. We extend our framework to by leveraging the so-called Eulerian Lagrangian formulation, such that we can capture the dynamic behavior much effectively. And by looking at that, we realize actually we are kind of like formulate a generic physics constraint optimization. So it's no matter what kind of object-oriented problem, control, optimization, or identification problem, you can set up objective, and we have our physics process like a constraint, like a physics constraint here, right? Of course, we have our neural representation to approximate either the unknown parameter. This unknown parameter can be very generic. It can be unknown boundary condition. It can be unknown material parameter. It can be a lot, right? You name it. And this is the solution. We also set up a solution. So I just want to pinpoint the key feature of our framework is mesh free. We don't rely on a finite element, which is really give a lot of flexible, and is a direct optimization. It's a neural network approximate field. So I probably will skip this. This is a backbone on our learning-based solver. We utilize the so-called Eulerian Lagrangian type of material point method. We're using that as our backbone solver, but actually we can also using like the previous, we based on the total Lagrangian type of material point method is also fine. But here we select that because this is already widely utilized for this Eulerian Lagrangian type of simulation. So I just want to show you that, of course, first, we still perform some comparison in terms of forward simulation to make sure our code development is legit, is accurate. So we compare this classical like a 2D granular collab, then we can accurately capture the behavior compared to the reference. Here we are using Zuckerberg elasticity model. And besides the accuracy, we are also very interested in the efficiency. So this is 3D like a cylinder collab example, contain more than 2 million particles. And we are surprised to see that we are simply using one GPU, but we are achieving 31 times faster than the classical Fortune like a solver, NPM solver. And not to mention, if the solver you are not implement the like parallel computing value enough, the difference could be hundreds. So we are getting the hundreds faster by using this neural network enable simulator. And okay, so I will just quickly wrap up the talk. Remember, the goal here is that this is a learning-based model. We want to achieve inverse modeling simultaneously within the same framework. So I would neglect some like a mathematical detail, but just the key idea is that it basically using the chain rule. Chain rule is implicitly performing the adjoint sensitivity analysis within the computation graph. And here we propose an idea to how to collect the data, right? For example, you can just visually see that we can collect the data Eulerian, which means it's fixed at the spatial point, or we can collect the data Lagrangian, just like we chasing the material point. If the material moving along the length lining, we're chasing that. So we can do either way. I just want to highlight the framework is very flexible. So we have a few examples. Actually, we have more. But in the paper, we present this example. For example, the first one, if we have unknown initial condition, and we can use a neural network to approximate this unknown, then we can see that our framework actually can quickly converge and identify the ground truth initial condition by our framework. So this usually is a very challenging problem for this large deformation Lagrangian type of landslide. You need to, for example, you only have the measurement at the final state, but you need to trace back to the initial state. Another example my student work on is with some spatial varying coefficient. Is interface problem. So this is quite nonlinear. So the system itself is a nonlinear material problem. And right now we are looking at the interface, whether we can recover this interface coefficient by our framework. So as you can see, along the training, actually some parameters quickly converge, and some are less effective converge, but still they're getting doing a good job. But it is very reasonable, because like for this red curve is corresponding to mu2 and mu3 is like a far end parameter in the last of a moment. So you can imagine a lot more error will propagate up to there. So it's harder to estimate, but still the final result looks very good. So this is some ongoing work. Is not published yet, but we are actually try to handle some challenging problems with the softening. If we really observe shear band, can our model still do the job? And we are getting a very promising result, as you can see here, for the no matter for local model, non-local model. But here we will try to sell the point for the non-local model. We have captured this shear band very well, and we are able to capture the inversion for the material strand. As you can see, our non-local model is hitting the exact solution quite well by this learning-based simulator. I am afraid I already run out of time, so I will skip the second part. Really sorry about that. I didn't estimate the time, but I will say the second part. The idea is that we are trying to utilize right now the latent diffusion model, because we are trying to do the inversion parameter identification for the permeability, or we call conductivity, for the subsurface, only with a few measurements related to hydraulic head. And we are using the latent diffusion model for the dimension reduction and for the generative sampling. And we encode a differentiable solver by the van der Waals method, and we perform the this AD type of optimization. So I will just give you some like a quick skim the result. Actually, we're getting a very good result by looking at different like correlation lengths. So we are predictive result is match this is a very challenging problem, because we are only taking 4x4 or 16x16 measurement. So we also compare to the previous work I done by using physics inform. So you can see physics inform, if given this super sparse measurement, you don't get any reasonable inversion result. But this new framework, we are getting this relative realistic result. And we have more example. And finally, we are testing on the by material with a sharp interface. Then you can see the latent diffusion model. It can provide more clear and accurate interface than the standard variation autoencoder model. More detail, you definitely can go to our this preprint to look at that. Then we can see through the increasing more measurement, then the immersion is increased significantly. All right. So the time is almost up. I want to conclude my talk with this slide. The key point here is that our group tried to develop this so-called hybrid differentiable computing framework by combine the neural network-based deep learning method with the physical-based numerical method. And we try to demonstrate we are not just can achieve fast and accurate simulation result, but it enable the data assimilation and inverse modeling under the same framework. And I envision this will pave the foundation to move forward for this digital transformation for all this civil geo engineering, and this is the promising realization of a digital twin by using this kind of methods. So with that, I thank you for your attention, and I would like to take any questions.